3.1 What is a wave? In physics, a wave is a disturbance or oscillation that travels through space and/or a medium, carrying energy and sometimes momentum without the bulk movement of matter. A mechanical wave is a disturbance that needs a material medium, solid, liquid or gas to travel through, transfers energy by causing particles of that medium to vibrate around their rest positions without the medium itself moving along. Difference between mechanical waves and electromagnetic waves. Feature: mechanical waves, electromagnetic waves. Medium requirement: require a material medium, solid, liquid or gas. Do not require a medium, can travel through vacuum. Particle motion: transfer energy via vibration of the medium's particles. Self-sustaining oscillations of electric and magnetic fields. Types: longitudinal, for example sound; transverse, for example waves on a string; surface, for example water ripples; always transverse. Propagation speed: varies with medium, for example approximately 343 meters per second in air for sound. Fixed in vacuum, c approximately 3 times 10 to the 8 meters per second, slower in materials. Energy transfer: particles pass kinetic energy to neighboring particles. Energy carried by oscillating fields. Examples: sound waves in air, seismic waves in earth, ripples on a pond, visible light, radio and TV signals, X-rays. 3.2 The wave model. In the wave model, a wave is a repeating disturbance that carries energy through space or a material without transporting the material itself. Every wave can be described by 4 fundamental properties. Amplitude: the height of the wave from its middle equilibrium to a crest or trough. Larger amplitudes mean more energy. Wavelength: lambda, the distance between 2 identical points on successive cycles, for example crest to crest. Frequency: f, how many complete cycles pass a fixed point each second measured in hertz, A's. Frequency equals 1 over period, f equals 1 over t. Wave speed, v, how fast the wave pattern moves, given by the equation velocity equals wavelength times frequency, v equals lambda times f. Examples: a wave on the surface of water has a frequency of 5 Hz and a wavelength of 0.8 m. What is the speed of this wave? V equals lambda times f. Lambda equals 0.8 m, f equals 5 Hz. V equals 0.8 m times 5, v equals 4 m per s. Sound travels through air at approximately 340 m per s. If the frequency of the sound wave is 680 Hz, what is its wavelength? V equals lambda times f. V equals 340 m per s, f equals 680 Hz. Lambda equals 340 divided by 680, lambda equals 0.5 m. A wave on a string has a period of 0.02 s and a wavelength of 0.5 m. Calculate the frequency of the wave. F equals 1 over t, f equals 1 over 0.02, f equals 50 Hz. Using your result, determine the speed of the wave. V equals lambda times f. V equals 50 times 0.5, v equals 25 m per s. Waves come in 2 main forms: transverse waves, where particles of the medium move at right angles to the wave's direction, for example ripples on a rope or water surface. Longitudinal waves, where particles oscillate back and forth in the same direction as the wave travels, creating alternating compressions and rarefactions, for example sound traveling through air or a spring. This model applies both to mechanical waves, which need a medium like sound in air, and electromagnetic waves, which do not need any medium like light in vacuum. By using the wave model, scientists can predict and explain behaviors such as reflection, refraction, interference and diffraction across many different situations. Types of waves in the model. Transverse waves. Particles move perpendicular to the direction of wave travel. Examples: ripples on a rope or slinky, surface water waves, light and other electromagnetic waves, by analogy. Longitudinal waves. Particles move parallel to the direction of wave travel. Examples: sound waves in air, P waves, primary seismic waves, in earth. Surface waves. A combination of transverse and longitudinal motion, confined to the boundary between 2 media. Example: ocean surface waves. Water moves in circular orbits. Real-world examples: sound waves. Vibrations travel through air, allowing you to hear music or speech. Ocean swells. Wind-driven ripples on the sea become large swells that move energy across oceans. Seismic waves. Earthquakes generate both transverse S waves and longitudinal P waves that travel through Earth's interior. Electromagnetic spectrum. Although EM waves don't need a medium, they follow the same key characteristic definitions: lambda, F, A, V.